So, good morning. I'm going to call the next by last name, and it's going to be alphabetical. Owen Berry, Jason Young, Jason, Lauren Drake, Brandon Cohen. Neil Clark, Kaden Cooks, Taylor, Aaron Butt, Anthony, Brian Gill, Madeline Black, Jason. Oh, I came on. Oh, okay.
Appreciate it. Thank you.
Alex, Leslie, Girl, Andrea. Ashley Henry, Ethan Coffin. Jay. Correct. Levi Dirk, Morgan Weaver, Jaden Lake. Brandon Mishra, Farida Mohammed. Yeah. Roger Null, David North, David Norris, April. Robinson, Lee Johnley. If it is another Robinson, that is what. Make more time. John Hill, William Soto. John, Jeffrey Wells, John Lloyd.
Benjamin. Daniel Long.
Samuel Zephyrus. Trouble last time. Here are the averages for the exam. The 6 students or science students between 80 and 100. There was one student scored full. Leslie, that was good work. And the total points. Remember, I do one curve parameter that I provide is 8. So that was chosen to be 15%. I return back some of the points for the whole course. It's not just for midterm, for the whole until now, whatever points you have and or whatever you have missed until now, I give back 15% of that. That's good. This time I chose to be 15, next time need not be that, it will be less or more. The total is decided with grade. Again, highest is 100. Average 79. So let's say A. From what I've seen, those who got 95 and above seem to be understanding the subject reasonably well. Doesn't mean that others are not, or maybe you're not working. Many factors that goes into it. But surely I saw about 7 students who did get on the top. Like I think their work was good, very good. In fact. So, any questions in general? Yes, please.
Should we go over
Number 5. Could you remind me, which one is it? Huh?
the square one?
Oh, again, that's the 5th time we're going to be going through it. This one. This one?
Yeah.
Okay. So. I'll say all the things, just for labeling purposes, let's say 2, 3, 4. And they're all same charges, Q1. Q2 actually, and the sign is the same. Q4, let's calculate the force on 2, 1 and 2 repel. So that's F on 2 by 1, right? On 2 by 1, so on 2 by 3. So the vectors. And this is going to be a little deeper because it's a little farther. And so that by let's F 2, 4. And yeah, so F21 is equal to it's purely on the x-axis. So whatever it is, let me call that F. I think that's how we were working on it. So and where F now I define F. F is K Q1, Q2, which is all the same. The Q, the K Q1, Q2, which is K Q square over how far you're from it, so that's L square. So that's the F that goes in there. F23 is in the y direction, so that's 0I, and it turns out to be exactly the same F here. Fj. And F24 is equal to, there's a direction associated with it. It connects, it is along the line connecting them. So along the line connecting them is the diagonal, so we know that this is a square, so that's 45 degrees. That will be 45 degrees. And the distance here is going to be square root of 2 times L. When you square this, that becomes 2 times L square. Overall, the coefficient becomes F over 2. And now we have to take care of the direction. So the direction is the sign 45 in the I direction plus same amount, but sine 45 in the J direction. That's what it is. So sine 45 is 1 over root 2 or root 2 over 2. However, you write that, and a total then comes out to be F 1 plus. So it's 1 plus root 2 over 4. Root 2 over 2, then that becomes root 2 over 4, and it's the same quantity that comes in here also. And the magnitude was also, I suppose. So magnitude of this is simply √2 times f, which is, it's okay even if you leave it like this, but it's convenient to write this as 1/2. And at this point, it is good to replace f with k³ of square. I was a little not lenient, I should say, on grading this because we did it so many times. Or it's not that we did it so many times. I saw the steps here, but it seemed like there was memorization. I didn't mind it was correct, but often it was, for example, f was replaced with q. And sometimes there is no f at all, there is just numbers. So I get the point, what you're doing, but then since it was already done, so I was not very lenient. You have to describe your steps, correct? And especially not description. If the f is not there, then it's wrong. So in that sense, I was a little correct. But if you had written it correctly, edit your points. It doesn't matter whether it's from memorization or not. I don't mind it. But then it has to be correct. Okay, so that's all. So, did that help? Okay. Anything else? At this point, can I again ask, was it reasonable? Okay. Yes. It's a ratio of the masses. So it comes out 1830 or 190. If it is 2 6 digits, it's 1900 or 1830. No, mass of proton over mass of electron. If it is opposite, you get it wrong. Let's talk about it later. Yeah. Yeah. Okay. We introduced the idea of electrical energy after having worked on electric forces for in the first few weeks. And now we want to see the same thing in terms of energy concept. And we introduced the idea of electrical potential energy and electric potential. It's very similar to what we have in forces. We have force and force per unit charge. That's the electric field. And energy per unit charge is called the potential. So let's write this down. Here we get a diagram now, right? That helps. So for a point charge, we have the force F. F is our hat K one Q2 over R square. A lot of notation that goes in this. This is the distance between the two charges. It doesn't mean that one of them has to be at the origin, even if both of them are not at the origin. This R is the distance between the two charges. R hat is draw the line connecting between or draw a line connecting the two charges. And this is, if it is both positive, that is in the outward direction from that line. So that's Coulomb's law. And we said there is a connection between that and electric field. And we talked about the simplest way of seeing that is force per unit charge. But more than that, we said that electric field permeates all through space. The moment you keep a point charge, there's an electric field at every point in space. And electric field for a point charge comes out to be, you just have to divide out by one of the charges. Let's specify this. Force on Q by 1 will be the charge Q2, and the electric field due to 1, where electric field due to 1 is R hat and K be 1 over R square. We have used this sufficiently. And force here is on a charge. So the moment you so it's very physical in the sense you have a charge Q2 sitting on it and you're talking about a force acting on that. Here, on the other hand, you're talking about an observation point. There is no second point as such. So when we say this is the distance between two points, there is one point is described by the charge. What about the other point? That's the observation point. There is nothing sitting there, but still there is an electric field associated with charge U1. That's force. And that's force per unit charge, which is the electric field. Energy, potential energy is equal to this. It's not a vector, it is a scalar, and it is equal to K Q1, Q2 over R. So again, R is the distance between the two charges. The moment you keep two charges, they start interacting between them, and that means that there is an energy associated with that. If you bring it, either if you bring it closer or farther, either it does work on you or you have to do work on it by you, means there is a change in the electrical potential energy. So this is energy. And again, you associate the idea of energy per unit charge, and we say this is potential. Well, we change U1 over R. So what's the connection here? So this is, let's call this V1, and potential energy is Q2 times V1. We also emphasize on the fact that usually it is only the change in energy that is important. Energy is off by a constant. So we are typically talk about change in energy. That's what is more well defined. Otherwise, you are at least saying that it is with respect to some point. Typically, in electrical quantities, you say, unless you are doing when you're an electrical engineer, you would say the ground is the reference point, but in these type of problems, typically infinity is what is chosen as a reference point. When we are doing potential energy on the surface of Earth, we say the reference for energy is the ground itself. When the height goes to 0, the energy is 0. Notice that when R is very large, that is infinity, this becomes very small, that is 0, and that's your reference point that at infinity, the potential energy is chosen to be 0. In this spirit of Q1, this is Q1. In that spirit, this can be said this is U21. So that's that it's the interaction energy between 2 and 1. The notations often it is not consistently used to write 2, 1, but if you want to interpret it that way, it is the interaction between charge 2 and charge 1 that's given by this. And you can, if you talk about energy per unit charge, this is the potential. And the moment you talk about the potential, there is only one point, and the other point is your observation point. But there are no two charges now, so there is no interaction. And the interpretation is that the whole space is filled with that energy, and one point is Q1, and the other point, if you want to relatively talk about, then it's the observation of energy and the force. How are they related? That's change in potential energy is negative of force started with being out, and it is initial to final. Typically, if it is the work done, then you have to specify the path, but this is the potential energy. I think it is independent of the path. You don't have to specify the path. Same idea here. This will be change in potential. Will be for the negative. The electric field dotted with out. Negative R. Change in the coordinate, change in the observation point if you want. I'm writing out so that I can use derivative in the next step. But our initial to our final. So as you move around from one point to the other, how much work is done by the force, right? If you're moving in the direction of the force, all the force is helping you move. But if you're going in the opposite direction, you're going against the force. So you have to the negative amount of energy. A change in quantity is equal to some quantity here times the differential element. That leads to the idea of differentiation. Remember, differentiation is the opposite of integral, or it's the inverse of integral. So if this relation is true, it should be possible to write the force in terms of energy. Same thing here, force in terms of energy. Here it will be the electric field in terms of the potential. So let's try to get that definition. So if this is true, remember, if you have, let's say, an integral of a function f with respect to x, that's equal to, let's say, g. That means if I make a small change in g, the differential in g will be equal to f times dx. These are g and f are functions here. So if I remove the integral, that means I'm making a small change in that quantity, and that will be f times dx. And then I can write derivative of g with respect to x would be equal to f. So derivative of, if derivative of g is f, then integral of f will be g. In that sense, they are inverse of each other. So if you know one, then the other is connected to that. This is very similar, except that this is not a one-dimensional differential. This is a three-dimensional differential. This is a vector. You can go from one point in space to anywhere else in space. So very broadly speaking, if I were to connect them, so let's go to the force. First, the force is equal to the negative sign, and the change is instead of telling this is a total derivative, since there are three variables involved, we use what is called a partial differentiation, and it is partial derivative of u with respect to position. That's not a completely correct notation, because you're saying you're dividing out by a vector. What does that mean? That's not very common. We don't define what a division by a vector is. But this operator has a meaning here, so let's use it. The correct notation is you don't write this. Instead, we use this operator. That's called a gradient operator. We introduced this in the first part of this course. This is the gradient operator. It just means that force is the change in energy with respect to position. It's a negative change in energy. Negative means that nature is always trying to minimize the energy. If you were in a world where every energy is trying to be maximized, then this will be a positive change in energy with respect to position. What is the gradient operator? This is just a short form for what is this 1 over dr? What does that mean? So that's equal to the change in x plus change in y in vectorial sense plus a. As far as interpretation goes, what you want to see is that first decide on a direction in which you want to talk about the change in energy. So if you have a region in space, this could be a three-dimensional space. First talk about dr. This could be any arbitrary dr, so that's dr. Sit on a point and decide in what direction do I want to investigate whether the energy is changing or not. So if I choose that as an arbitrary direction, and then find out what's the change in energy. So change in energy in a particular direction. In that sense, this is also called a directional derivative. It's not a normal derivative, because in three dimensions you are talking about in what direction you want to go. First decide on a direction and then do the normal function. So it's a standard same derivative of a function, except you first decide what direction that dr is, and that dr direction is in a sense the denominator, right? So it's 1 over derivative with respect to x, 1 over derivative with respect to y. So it's a directional derivative. When the partial derivative means that when you're taking a derivative with respect to x, you don't worry about that. Everything else is a constant. So just for reviewing purposes, d by dx of x cubed y plus z squared x4. This is equal to. Then I'm doing this x. This is the only x matter there. Y is just the spectator. And I'm doing doesn't have for z, so z squared is a constant. That's 4x3. That's how you do these operations of derivative. So everything is constant except for the variable we're talking about. So in that sense, this partial derivative is different from the complete derivative. If it is a single variable function, it doesn't matter whether it is partial derivative or total derivative. So it's the same. So that's your force. But once if you have a force idea, immediately can say the same thing about electric field also. Force is a change in energy with respect to a change in a coordinate direction. Here, electric field will be a change and negative change in the electric potential with respect to a direction. And as I said, that's not a common notation. You don't divide it by a vector. That's more correctly, or in the correct sense, that's definitely this is not common. So that's called the negative gradient of the electric potential is the electric field. But at this point, this is not the electric potential associated with the two charges, then one of them is an observation point, right? Electric potential 0 point charge at another point, which could be anywhere, so it is spread out in space. Notice how this comes out. We spent a lot of time on calculating the electric field for certain geometries. The most important geometry is, of course, the plate, the flat plate, where the electric field comes out to be a constant. It was best described using Gauss's law. But here it might be easier in a sense that this is dependent on a scalar, and often scalar quantities are easier to calculate. So maybe one can calculate the electric potential due to a plate and then take a derivative. You could get the electric field. When electric field due to a plate is known, it is a constant, right? So remember, planar configuration, so say plate, electric field is equal to sigma over, if it's a dielectric plate, it's 2 epsilon naught. But sigma is charge per unit area. And if I were to draw this, or say, as a positively charged plate, right, it doesn't matter, it could be distributed everywhere on the right side, and this is infinite, this is of infinite extent. So it extends all the way to the top and to the bottom, and somewhere here the electric field is pointing outward. So let me draw the electric field lines. That's the best way to describe this. That's your field lines. So since they are equidistant or they are all parallel, that means the density does not change, so it is perfectly uniform. And that's what it means. This is perfectly uniform. I can also specify the direction. The left side is a vector, so right side also should be a vector. But that's a symbolic way of representing it. That's n hat, where n hat is this side. That's for completeness, that left side is a vector, the right side should be a vector. And that symbol means that it is perpendicular or normal to the plate. We should be able to get this same idea by calculating the electric potential now, not the electric field, electric potential everywhere around the plate. So we should be able to start with a point charge, build a plate out of it, and then take a derivative of that function, the electric potential. That should give us this formula. So the question comes, what is the electric potential for a plate? That means derivative of what quantity gives you the electric field. So that in that way of putting it, it seems to suggest that it should be linear, right? If you want to get a constant out, that must be linear. But now there is more freedom here because this is a three-dimensional space. If it is one-dimensional, it is purely linear. But now, if it is three-dimensional, is it really linear or not? So let's investigate that. So let's take this plate and open or view it from the top of the plate. So that's your plate. And this is of infinite extent. And we would like to put a charge Q on it. And then talk about charge per unit area. This is of infinite extent. That means the total charge Q on it has to be infinite. But the area is also going to be infinite. So charge per unit area can be fixed. So sigma here be equal to Q over the area. So that's large. By that I mean really infinite. If you're talking in two significant digits, if you're 1 centimeter close and this plate is about a meter long, that means two significant digits. That's pretty much infinite. So in that sense, this is a large quantity divided by a large quantity in such a way that this remains a constant. So it's a well divided defined quantity, ambiguity in there. This we will notice that this electric potential that we are going to calculate is going to have a infinite concept associated with this because of the largeness. So let's make this small, and in the end, at the very end, we are going to take it to infinity. So instead of talking about a plate of infinite extent in this form, we change the idea, so we make it a disk, which is of a large radius. Now a finite disk. But the idea is that R is going to be large. R is going to be large. Notice this quantity, this is a square of infinite side of infinite side lengths and a disk of infinite radius. So this is a disk but a square. Same thing. As far as they're infinite, there is no way you can reach the end. So for our purposes, they are our mathematical purposes, they are exactly the same. And we will deal with this just because the integrations are going to be slightly more, we will be able to deal with the identities that we have already seen in a background course here. Sigma then here will be equal to the total charge remaining Q, but this time it is finite. So unless I take the limit r tends to infinity, so Q, but then it will be large, right? So I'm going to take it to infinity anyway. And now this has a more clear picture here. So it's 4 pi r squared. Here this would have been L, then take the L tends to infinity. It would have been L square there, and then you take the limit L tends to infinity. 4 pi r squared it is. Where I say wrong? Pi r squared. Oh, because it's a disk. Yes, sorry. Yeah. Very good. Thank you. Thank you. Yeah. Be more confident. Yeah. Now you are. Yeah. Pi r squared. Polite. Thank you. Now it's better. Yeah. Okay. Thank you. So the point is this is a disk. So its area is pi r squared, not 4 pi r squared, as we carried on, carried away by the sphere. So it's pi r squared. Thank you. Let's we want to do an integration, so we want to split this into tiny elements. So we want to build this in the following way. So this is the same disk, but now I am going to hopefully this thing sort of. Yeah. So this is a tiny element inside that disk. So that's your radius r, and let's say that's small radius r. Okay. When I say the charge per unit area is uniform, I can pick any piece out of that disk. What does it mean to say that something is uniform? Is that pick any piece out of it, whether it is small or big, and it should have the same ratio of charge and area. So surely one piece we took is the whole disk itself, and that's total charge Q over pi r squared. But this time we pick this tiny ring in a science. And if I cut open this ring, if I cut open the ring, this has a length on the side which is dr. So this is dr. That ring has a thickness of dr, differential element. What is the length of that ring? That's the circumference of that circle. That's 2 pi r. And the charge on that, in that strip is also supposed to be the same. So this will be equal to how much charge is there? Let's say the charge on that ring is dq. So that's dq over, now the area of that strip, which is 2 pi r length, times the width of it, which is a differential, which is a tiny element. So this also should be correct. And you can take any piece out of this, then it's always uniform. So that's a relation we have developed just from the fact that this is a uniformly charged disk. Just that information is from that information we are able to tell us. This tells us that dq, that element on that charge ring here, is proportional to the radius. It's not the same amount of charge on every ring. Of course, at the outer ring there will be more charge because it is having a longer length. So let's put this all together and we can say that dq is equal to multiply this. So that's sigma times 2 pi and r here. What that does is that it tells me how much charge is there in each of that radial element. So I divided that disk into many radial elements and it tells me how much charge is there in each of them. And now the strategy will be, our goal, remember, is to calculate the electric potential due to a plate and then take the derivative of that or the partial derivative of that and try to get the electric field. But we are going to do that for one ring and then integrate over all. To calculate the electric potential due to one ring that I have drawn there and then add up all the rings. And where are we calculating the potential? Let's do it on an axis. Like there is an axis for this disk. The moment you say it's a disk, there is a line that is perpendicular to the disk and going through the center. So that's the axis of the disk. And let's calculate that. It doesn't matter whether your axis or here, because when you take a limit happens to infinity. So origin has, there's a lot of advantages of being on the axis. There is a lot of symmetry there and things become simpler. It becomes relatively harder when you really move it away. If the R is of finite length. So these are all calculations which are very dependent on the choices we make. But it is okay in the end, since R is going to be infinity, it doesn't really matter. After that, you can move around wherever you want to. So let's calculate the electric potential you are in. It's a relatively long exercise, but there are pieces that we have already come across. So now we are talking about electric potential. It's the same exercise, but we are taking a diagram and talking about electric potential. Due to a ring. So we pick one ring of that and we want to calculate electric potential due to this ring. This is of dr length, but that's a ring for now, infinitely thin ring, and that's your axis. Let's say this is a radius r, because that's what we had. That's radius r. And let's say this is S. That's our observation point. By observation point, we mean very quickly you could keep a charge there and talk about what the energy are at force. We're saying this is uniformly charged ring. The total charge on this for the time being, let me say is some q prime. That should be connected with dq there, right? I don't want to write dq here because the differential will can be confusing. This dq in that context is just the total charge, that is q prime. So for our purposes, this is actually equal to dq. This is part of another problem that's actually dq there, but as an independent problem, there is a total charge q prime on that way. That's all that means. But later on, we'll connect it to the charge dq. So that's q prime, and I'm interested in calculating the electric potential here. No vector. Earlier, when we were doing it, we would say there's a positive charge there, there's a vector, but now it's a scalar. Electric potential is a scalar quantity. I just have to add the contribution to the electric potential from every tiny element here. That's a tiny element. That's another tiny element. Keep adding all the tiny elements. So let me talk about this point here. So let me say that's dq prime. Not to be confused with that. So let's say factor q prime. Be safer with the confusion. That's dq prime. This is q prime, a small element of that capital q prime. The potential contribution, a small contribution to the potential due to the small tiny differential charge will be k times dq prime. Remember, potential is k times q over the distance. This is distance, but not s. That's it. And that's the contribution to the potential due to the tiny element of charge, differential element of charge q prime, and it's the appropriate distance you want to keep, s. If I want the total potential here because of the whole ring, I have to integrate this over that whole ring. So integrate this v is equal to the total. Add up, right? Add up all these tiny elements. That's what the total potential is, and that's over the ring. So you're integrating over the ring. Since there is no variable, that this is a broad potential variable, so I have to tell it in words instead of actually putting the limits in there. That's equal to, while I'm here, I'm actually integrating over this whole ring, whether I'm at this point, or at this point. All this is a complex cone, and these are all of the same length. That's the advantage of being on that symmetry axis. If I was not on the symmetry axis, that wouldn't have worked. This is a right circular cone, and each wherever I am a distance x from the dq prime. So when I do this integral, all this comes out, and what I have is k over s, and integral of dq prime. That happens only because you're on the symmetry axis. There is an argument here that went through that this integral has gone into the, or f has come out of that integral. That happens only because you're on this right circle, only because you're on this axis, and the point on the axis is equidistant from every charge. So x is the same there, and that makes it this is kq prime. This is now the total charge kq prime over s. Let's write the x in terms of r and some distance on the horizontal axis. Let me erase this. So now there is a right triangle. This was r, and let's call this z. How far you're from the disk. So you would eventually like to say what is the electric field at that point. Z there. And in terms of that, x is nothing but v squared plus r squared. Squared. That's the electric potential due to a ring. How much charge there is on the ring? divided by the length in the sense that it is the hypotenuse that is formed from the right circular cone that you construct from that axis. If you want to write it in terms of C and R, it will be convenient for us because we want to now talk about various rings. We want to integrate over R, so we replaced it with that Z square plus R square. This is nothing but AQ prime over S. It's almost like saying there is one charge at a certain distance F, the point charge would have done the same thing, but this is a ring at this point. So now we know the electric potential due to a ring, and now we come back and work here. Now we add up all these rings. We now know the contribution due to one ring. The disk is a sum of rings. So the potential due to a disk of radius R is equal to integral of dV due to a ring. I add up and I add up in such a way that I'm integrating over the radius R. I get the contribution from each of those rings. So this is equal to this time. I replace this dV. Now this is the potential due to a ring, but this now I have interpreted as dV, and that means I have interpreted this as a small element C prime. But then I'll remember that for C prime of dQ. So I'm replacing. So now V was equal to K Q prime over S, but now I change this to dV is K times dQ over S. So instead of taking a total potential, that's a differential potential now. I read that as a contribution due to an infinitesimal ring. So that's equal to K and dQ over S, which now is d square plus R square. Oh, I wrote this wrong, right? I wrote this as capital R, but this is small. I wrote this capital R, that should be small. Replace your dq. Remember, we said how much charge is there on each of these rings. We calculated that to begin with. That was the reason why we investigated that. So that's equal to K times sigma times 2 pi R divided by R square or Z square. And now I can put in the limits because now it is not an integral over a charge, it's a geometrical idea. I have replaced the integral over dq, which by virtue of saying that you add up all the tiny contributions from the tiny charges. Now you're saying that this is integrated over the radius R. So now it's a geometrical idea. I can say R is equal to 0 and R equals capital R. That's your limit. You go from the 0 point on the disk to the outer point on the disk. So that's R. K is 4 pi epsilon naught inverse the 4 pi epsilon naught. This 4 pi cancels the 2 pi. There is a sigma over 2 epsilon that's coming out. If you remember, this is the electric field that's showing up here, but it's still an integral. And this is the potential. Now this is not the electric field at all. So that's 0 to R dr over Z square plus R square. When you do this integral, okay, reasonably straightforward integral. Let's quickly do this here. So I can substitute z square plus r square is equal to t. Z is just a spectator there, that variable is not changing. So then you say this is 2 times r is equal to dt. And that integral this becomes when r is equal to 0, t is equal to z square. So t is equal to z square and t is equal to z square plus r square. That's my limit there when I make that substitution. R times dr is dt by q. And z square plus r square is nothing but square root of t. That's an elementary integral now because it is t raised to half. So remember integral of x raised to n. The x is x raised to n plus 1 over n plus 1. So this is t raised to minus half. So I can do this integral. This is what that is equal to. And this is equal to t raised to minus half plus 1 divided by minus half plus 1 is 1 by 2. But there's already a 2 there. So the 2's cancel out. This is equal to square root of t, which I have to evaluate between z square and z square plus r square for t. So that's that integral. You can use that, do that as a table. There are other substitutions you can do. However you do it, you evaluate that integral and you get the potential for the disk to be equal to sigma over 2 epsilon naught. This integral, when I evaluate this at the 2 points, this is z square plus r square and minus of z square, which is nothing but z itself, which you should read it as magnitude of z, right? So we read that as the magnitude of z. Depends on whether you're on which side of the disk are you on. So where is the z here? I should clarify what that z was. We were a distance z from the plane, so that's your z. So the electric field is independent of that z. So when we take the derivative, it should go away. Remember, we thought it might be linearly dependent on z. It is linearly dependent on z, but now there is the feature that what happens in the limit r tends to infinity. Like we would like to think of this as a full plate, and then you encounter a problem here, because this is a very large quantity there. In the limit r tends to infinity, this z is not there. This is imagine this is a million and this is a micrometer. This doesn't exist there, so it's just r. And in the limit r tends to infinity, this is a very large number, and then you're subtracting a very small quantity out of it. If you take the derivative of that, it might contribute. That's the whole idea, but this access is not very well defined for r tends to infinity. So this seems to be not very well defined. Only for r tends to infinity. For the disk, it is okay. In the limit r tends to infinity, v is infinity. So it's an infinite quantity. And you might give up there, but then we are talking about the derivative of the potential, which is the electric field. And if you keep r a constant, keep it very large, but keep it a constant, then that derivative it doesn't contribute. Remember, potential is off by constant all the time. And this is that quantity that might not be contributing to it when you're making a change. It's like talking about two very large quantities you're subtracting, but then you can still take out a very unambiguous small part out of it. So let's see if that really works. So we should be able to see that if we take a derivative of this, that was the whole exercise here, that the derivative of the potential should give you an electric field. So I calculated the potential explicitly, except that I did not take the limit r tends to infinity. We get this. The derivative of this should be the electric field, which we know is a constant. And it should just come out this quantity in here. So let's see if that really comes out or not, and if this exercise goes through. So we have electric field is the negative gradient of the potential. This is the negative gradient that has this ijk. So there are three derivatives involved in it. Three derivatives. I hat take a derivative with x, then you take the derivative with respect to y, and then you take the derivative with respect to z. Of the potential is said is sigma over 2 epsilon naught, and this is v squared plus r squared minus v squared. Seems big, but all of this is going to go away, and this gives you a very simple answer, but that gives the idea of electric potential very well. Notice there are three derivatives. I have mapped x on this, y on this, z on this. What's the derivative with respect to x of a quantity which does not have x in it at all? Right, it's 0 because there is no x in it. It's a constant as far as x goes. So this doesn't contribute. That's 0. Same thing with y. There is no y there to operate on, so it cannot operate on that. So it will give you a 0 there. So that's equal to 0. So my electric field will be k hat. The characters of k hat times, this is a constant that comes out of it. So sigma over 2 epsilon naught. That's supposed to be the electric field, but k hat is the direction perpendicular to the plane, and the derivative then is supposed to be 1. And again, I emphasize that before I take the derivative, in the limit r tends to infinity, that's a very large number, it goes to infinity. And I could also say that we have to take the limit r tends to infinity there. Okay, so take the derivative sigma over 2 epsilon naught, 1 over 2, the 1 over 2 on the power of z squared over r squared, then it goes in the denominator. And then you have to take the derivative of the argument, which is 2 times c. Derivative with respect to c, r does not depend on c. 2 cancels out. And minus of the magnitude of z, let us say z is greater than 0. So let me constrain myself to z greater than 0. It just changes the sign. If z was less than 0, it just says that it is in the backward direction. If you are on this side, it's display of finite, and the electric field is here. That's that negative sign that we are getting. And did I miss something? I missed this negative sign, right? I just copied that down here. So this is a negative sign. And if I'm in the z greater than 0, this is just 1. Now take the limit r tends to infinity. This is more well defined. Now the limit r is in the denominator. All this leads to the idea that it goes to the denominator. This goes to 0 now, and the limit r tends to infinity. Right? This is often infinity goes to 0. So you get negative and a negative, you get k hat and sigma over 2 epsilon naught. The same argument, same integration goes through when you're doing it for gravity. That's why the gravitational field is 9.8 meters per second square, and there is no radial dependence. As far as you're close to it, that's why what goes through. This was a long calculation. My apologies, but I think it is necessary. But in the last 5 minutes, I want to do a small example which will bring out the how you can use electric potential energy is its idea to in practical scenarios. This is also related to the problems that we talked about. In the first week or so, we had two spheres, and there was a nice discussion that was brought up during the review session that what if there were three spheres? And let's take a simple sphere, and let's talk about what is the electric potential at the center. What is the electric field at the center of the sphere? Let's say this is conducting now. This is conducting sphere, and there is a positive charge on the surface. Could be a conducting or it could be a shell. Either way, what is the electric field at the center? I'll emphasize this many times here. It is 0. Right? Electric field is 0. Say that again. But now the question comes, what is the electric potential there? What about V? Is it 0 there or not? So remember, electric field is equal to 0 inside. And if you're outside, it seems like it is a pointer. It doesn't have for the radius R at all. So it's only the observation point R that comes in. Observation point. There is no reference to the radius of the sphere at all, and it is R hat times K, let's say Q on this, KQ over R square outside. But that leads to the question, what about the electric potential? Remember, electric field is negative gradient or derivative of the electric potential. So we are saying that it is 0 everywhere inside the conductor. So that means the change in potential is 0. If you want to get a 0, what should that function be? Derivative of what constant gives you a 0? Constant, right? It should be a constant. So that means V should be a constant. So V is equal to a constant inside. And outside is that of a point charge, right? So it is KQ over R outside. That's exactly like a point charge. But what is that constant? Once you know that it is a constant, you just have to calculate somewhere around that sphere, very close to that sphere, and then that has to be the same. And on the surface of the sphere, we know the electric potential, so this is also equal to KQ. So now we have a reference to the radius R. Earlier, electric field did not have any reference to that radius R. Now, this is KQ over R inside, everywhere. Inside and on the surface of the sphere, it is KQ over R. And inside of that and outside, it is KQ over the observation distance outside. That's a deduction you can make in a very straightforward manner. And then you can ask, if you have two spheres like this and you connect it, what is the electric potential on that, and the governing principle is that the potential has to be the same. It's not the force. Earlier we said that force on two charges should be zero. It's actually the electric potential, because if there is no potential difference, there won't be any force. So it is the energy that has to be, or the change in energy that has to be the same. And we will talk about that more in another context. Thank you.
Very satisfied?